the easiest of my life to introduce. This is Longpan Chen. He's from the House of Love Institute, and he's presenting the work he did in collaboration with these fellows here from Microsoft Research and as well. So let's hear about even more clever stuff about haptic retargeting in flight.
Thanks, Pedro. Right, so I'm Longpan from House of Love Institute, and today I'm going to talk about Sparse Haptic Proxy, touch feedback in virtual environments using a general compressive prop. And this is a research project I did when I was interning at Microsoft Research. And here's how Sparse Haptic Proxy provides touch feedback. The user is immersed in a virtual cockpit, touching different buttons, but in reality, the user is actually touching the abstract hemisphere prop on the right, which we refer to as Sparse Haptic Proxy. And the main contribution of our work is that one Sparse Haptic Proxy not only works in one virtual environment, but generalizes to multiple. Here, the user is inside a different virtual scene, touching different objects, but in reality, he's touching the same physical proxy. And of course, the hemisphere prop does not exactly match all virtual environments. And here you can see the virtual overlay of the prop in the cockpit scene. And you can see the discrepancy between the virtual scene and the physical prop. And for example, the virtual button here is not at a position where the user can feel the physical prop. And that's what I'm going to talk about today. How do we achieve that a single sparse haptic proxy accommodates to multiple virtual scenes? And let me zoom out a little bit and talk about our motivation. And people have dreamed immersion for a very long time. One of the pioneers is the inventor of the head-mounted display, Ivan Southland. And people have worked on several challenges that come with immersive environments. One is to show photorealistic graphics. Another is to play surrounding sound. And also to give the users their body in the virtual world. And thanks to all the hardworking people who has the same dream, now graphics, tracking, and sound are almost ready to everyone. But there's still something not yet ready. We still cannot feel the virtual objects through these commercial devices like Oculus Rift or HTC Vive. So how do we advance haptic feedback to the same level of fidelity? And we're certainly not the first one asking this question. So researchers have been using machines to provide haptic feedback, and many people call it active haptic devices or active haptics. And one example is to use exoskeletons, machines that provide force directly on the user's body parts. And another example is to use robotic arm to just change the physical layout where the user is touching. However, because machines are complex, expensive, and sometimes dangerous, most of them still stay in the research lab. And in the meantime, researchers have been using props, just like what people do in a theater play, to let the users feel and touch virtual objects. And props usually are static, without any machine inside, therefore simpler and cheaper. So people call it passive haptic devices or passive haptics. And one of the earliest examples is from Ken Hinckley et al., where they use the passive doll head as an interface for browsing the brand images. And researchers have shown passive haptics highly increase the immersion and thus are used for military training as well. Here's an example from Iowa State University where they recreated the virtual environment with the physical props. And all those bricks and walls and all the equipment are passive props. And instead of just making a new prop to fit the virtual world, researchers also tried the other way around by matching the virtual object to existing physical object. But the main drawback of passive haptics devices is that one prop can only be used for one virtual object at one position. And consider this video game. And if we have a complex virtual scene like the cockpit here, we have to find a physical button for each virtual button to be at the same position. And this means that we need a lot of replication. And what we saw last year here at CHI is a simpler approach towards this. We're using a single physical prop by visually misguide users' hand motions. And this work explores several strategies of haptic retargeting, and here's one called body warping. The user sees his hand touching 3 different virtual cubes in virtual reality. But actually, the user touches the same physical cube every single time. So one physical cube for many virtual cubes at many positions. But now how about other objects like walls, floor, etc. in more complex scenes? So our goal here is to make all objects touchable, and all touch feedback comes from passive haptics plus body warping. And if we only focus on single finger touch now, many objects consist of surfaces. For example, the cube consists of 6 surfaces in different orientations. So let's just approximate them with surfaces first. So Sparse Haptic Proxy is a library of different surfaces that approximates all objects by redirecting the user's finger to touch an appropriate surface. And here's the example of one Sparse Haptic Proxy, a hemisphere that consists of 25 surfaces in different orientations. And what I'm going to show you is that this hemisphere approximates not only this virtual cockpit, but also the virtual room, which has many different items in it. And here's how it works behind the scene. We are doing 3 things. Firstly, we use an eye-tracking head-mounted display to predict where the user is about to touch. And secondly, we dynamically map this target to an appropriate location on the haptic proxy. And then finally, we redirect the user's hand to actually touch the proxy at that position. And here you can see the offset between the virtual and physical hand. And the blue hand is actually touching the proxy, while the virtual hand is touching the button. And for a scoring wheel, our system actually maps to the entire area to a surface with a more similar orientation. So our virtual reality system consists of an Oculus head-mounted display that incorporates an SMI eye tracker. And the user is tracked by an Oculus camera and combined with an overhead OptiTrack system. And as I mentioned, we are implementing Sparse Haptic Proxy in 3 steps. And let's talk about the first step, target predicting. So to use body warping from previous work, haptic retargeting, the system has to know the position of both the virtual target and the physical target way before the user is touching it, in order to generate this progressive offset between the virtual hand and the physical hand. However, if there are many things that the user can interact with, like the cockpit thing here, how does the system know that this button is actually about to be touched? So the system should somehow predict the target. So we found the previous research has shown a pattern of hand-eye coordination with performing a targeting task, where the user's eye gaze focuses on the target before reaching it. So we think this hand-eye coordination pattern could be used for our prediction. So that's why we used an eye-tracking head-mounted display to get the user's eye gaze, and also implemented a prediction state machine based on the hand-eye coordination pattern. And only when the user's gaze is fixed and the hand is starting to move, then the system can predict the target. However, we still don't know if the hand-eye coordination pattern will be changed by the body warping or not, because the change of the hand movement might distract the user and thus affect the gaze. So we conducted a study to evaluate the prediction. And this is a short clip of how the study looks like. So participant was instructed by the system sound to touch one of the targets while wearing the head-mounted display. Yeah, and the label on the target was randomly assigned for each trial, so the participant really had to seek the target. And to get body warping involved in each trial, the system changed the physical location of the target to a new location among these 9 candidates, no offset plus 8 different offsets in 2 different amounts and 4 different directions. So we recruited a group of 12 participants for our study 1, and here's the confusion vector we got from our study. So each target was touched with 9 different offsets by 12 participants, so 108 in total. And in average, our prediction accuracy is 97.5%, and the prediction is made 2 seconds before reaching the target. So this means we have enough accuracy and time to do the body warping with our prediction. And we didn't see a significant difference between different offsets Therefore, we conclude that the body warping has no effect on our prediction, and we implement it in our final system. Now, step 2, mapping to the proxy. So remember that the system has to know the position of both the virtual target and the physical target in order to do body warping. So by our prediction, the system knows the virtual target, but where should the physical target be on the proxy? So we came up with 3 different ways to map the virtual target to the location on our proxy. And the first one is called line of sight, which uses the point where the user's line of sight intersect with the physical prop. And this strategy minimizes the angular offset between the virtual target and the physical location. And the second one, as its name suggested, uses the closest point from the virtual target to the prop. And this strategy minimizes the distance instead. And the last one, similar normal, which maps to a location where the surface normal is closest to the virtual target. So we want to know which strategy we should implement in our final system. So we conducted another study to compare those. And here's a short clip of our study 2, just like study 1. The participants wore the head-mounted display and touched the targets, but this time only one target at a time. And the targets are arranged in 2 different layouts. And we shuffle all the possible targets and give one to the participant in each trial. And participants tried one strategy at a time, and the order is counterbalanced. And here's the result. And as you can see, most of the participants prefer the line of sight strategy, and they said that they felt more natural because less reduction was involved, despite there was a mismatch between the surface normal. And in fact, from the bar chart here, we can see the participants could hardly tell if the surface filled correctly or not between these 3 strategies. They even gave higher rating for the line of sight strategy. So this could be the reason that we only focus on one single point touch. The touch duration is too short for the user to recognize that the surface orientation. But for longer exploration, such as dragging on the surface, maybe to a similar normal will be still needed. So that's why we need this 3rd step, redirection range. So some element like the virtual scroll wheel should be mapped to a similar normal because the user is gonna drag around the surface. But in which range should we find the matching surface to guarantee a smooth redirection? So we conducted our last study to learn to which extent the redirection is still tolerable for the users. And just like the previous studies, the users wear the head-mounted display and then touch the target in the virtual world. And they gave the 5-point Likert scale for each trial. And also we record the time when the user touches the target. And each virtual target actually has an offset from where it actually should be touched. And there are more details in our paper how we designed the study. So basically there are a bunch of different offsets we generated to that the user to do the task. But here's the result. So we could imagine the larger the reduction, less scroll, and more time needed for the user. But we found no significant difference between 8 directions and 9 physical locations, both in rating and time. So it all comes down to the offset. Here we show the rating population in different offsets. And interestingly, if we see the non-offset bar, participants sometimes couldn't tell if there was a reduction, even there wasn't. But we can see that score drops dramatically as the offset increases, especially between 30 degrees to 40 degrees. So in order to guarantee a smooth redirection, we pick 40 degrees as the limit for our final system. Right, so we have presented Sparse Haptic Proxy, including the concept itself, a series of studies to realize it, and finally implemented as a working system. And we only focus on single point touch now, but in the future we would like to extend it so it can support object manipulation or multi-touch as well. And here's one of our demo experiences where the user tried to find a way to open the safe by touching different things in the room. Yep, that's it. I'm happy to take questions.
Please line up for questions.
Hi, I'm Mohammed Sayed. That's an incredible work. I have one question about the appearance of the hand, it is from the wrist. So is there a specific reason why it was chosen? Because the haptic retracing work had the arm displayed from the shoulder. So
Yeah, so basically, one of the limitations of the body walking is we change the body orientation as well. So that's why we only show the virtual hand here, because we don't want to distract the user. Actually, their body actually be rotated.
so in bigger offset, you mean the body will be like weirdly warped?
Yeah, it will look like your body actually rotated a little bit. Yeah.
And in the dome, the shape of the dome that is chosen, does it contain some of the materials so that they feel the buttons?
Oh, no, those are just like plain surface. There's no like mechanic behind it.
Cool, thank you.
Hi, Proxy from Stanford University. Great work. I noticed different virtual objects are at different distances from the user. Did you study the range for which you can kind of have this illusion work in terms of how far you can?
Oh, you mean the forward direction?
Yeah, because I think you studied the range of angles, but I was curious.
Yeah, that's actually a very good question. We didn't do a study about how far we can redirect the forward direction yet, but that's actually one thing we could do in our virtual world to see how far away the future actually will feel unnatural when we redirect forwardly. Yeah.
I'm Dustin, in charge of media entries in great work. Thank you very much. And just a question for the haptic redirection, you always need to somehow pull back your hand to a certain degree. So if I understood it right.
Yeah,
So,
yeah.
And what about if I would like to have, say, smooth motion? For example, you have a cube and you first touch this side, and then of course you don't go back to touch this side afterwards, but you just do it directly. So you have a more natural motion.
Yeah, that's a very good question. And I haven't mentioned in the talk yet, but we did discuss in our paper. So we changed the body warping a little bit. So actually it updates. Because you know that every time we do haptic retarding, we need to retract our hand, right? But actually we modified that part a little bit. So right now the body warping can actually support like you touch different objects directly without retracting your hand. Yeah, but that's described in our paper. Yeah.
I had a question, but we sadly out of time.